Wassim, I definitely want to give you plenty of time to talk, but I also wanted to just say thank you to yourself and to Topologic. I know it's um, a research development from Cardiff University and UCL, and the work you guys are doing is really pushing things forward. So thanks for that. And I personally want to hear more about that, want to hear about Blender BIM, and then the ways you've put that into effect in Dynamo and Grasshopper. If I'm correct, before we get started, we're going to talk for a couple minutes about theory, about application, and then we'll get into some of the practical applications later on. Is that kind of right? And we'll try to keep this conversational to help you guys as much as we can.
So basically, this is not my work. This is the work of a colleague called Bruno Postel, who I met online, and he had a piece of software called Homemaker. And we looked at it, we started chatting. It works in Blender, and it's really amazing because you can go from something like what you see here on the screen, which is just these types of cubes, but there are these kind of strange lines inside, and I'm suspecting those are what we call dual graphs. They are the kind of representations of the connectivity between the objects that you see, and this is what Topologic is about. So he had written this whole software called Homemaker that had nothing to do with Topologic, but then when he learned about Topologic on a website called osarc.org, he decided to port all his work and use Topologic. So in order to do that, I had to make Topologic available to him in Blender, and that means I had to move it to Python, and that was the thing that consumed my time over the last few weeks. So, but just to show you Homemaker, you can go from what you see here on the screen to fully detailed without touching anything. Basically, it's all generative. It's all based on shape grammar rules that he has encoded. And the idea behind Topologic has always been that you can set out the kind of rational basis of your design, not worry about all the details, because software is actually has reached a point where it is better than humans in populating our kind of virtual worlds. And you let software handle the complexity of adding all these elements and all these IFC objects that you see here.
So the human is basically putting the cubes around and then defining the rules that exist between them. Is that what you're saying? And then all the detailing and everything else is coming out automatically.
Isn't that what designers would like to do? Is that they would like to focus on the important stuff, which is what Vitruvius would call the setting out of architecture, right? You would like to design the strategy of how you would like things to be created, but you would like to do that in a very fast way, and but in a very rigorous way, in the sense that the system behind the scenes knows exactly what is next to what is on top of what, and can build these type of topological relationships so that you can ask it intelligent questions and it can answer them really quickly for you. So yeah, that's what it is really. Right, so we titled this theory and application, but before I kind of dive into the presentation, I should introduce obviously the team that worked with me on this. This project was a research project funded by the Leverhulme Trust. It was a project by Cardiff University and UCL, as Simon has said. And I worked on it together with Robert Aish, who I give a lot of credit to because he is the one who introduced me to the concept of what we call non-manifold topology, and I'll explain what non-manifold topology is. And it was really a workshop that he did in London at a certain point where at the end of the presentation, he mentioned this concept called non-manifold topology in a very, very small demo that he did. And it was a capability that he worked on with some people in Autodesk that was available in the precursor to Dynamo. And unfortunately, when they moved to Dynamo, they had to take that capability away. So I approached them and I said, how about if we write a proposal and we write something that is larger than what Autodesk had on offer, more open source and maybe platform agnostic, so we can install it on different platforms. And that's exactly what happened. It took us obviously from 2000 and I'm going to say 2016 is when we got funded to 2019 when the project ended. And now we have Topologic running on both Windows, on Linux, and on Mac. So it's really fantastic to see it running on all these platforms. Just to acknowledge also Simon Lennon, who joined us as a co-PI or co-I on it, and the two research associates, Katerina and Nicholas, he was the main software developer before he left to Japan. So should I just dive into the
Yeah, I think so. I mean, I think you're going to get to it, but for those who aren't familiar with Topologic, I mean, I assume the people who are watching this, they're very familiar with AEC, computational design. But is there like a couple things that you want to talk about, or are your slides going to get into the kind of basics of what even this is, this non-manifold topology and all these words you're using?
Yeah, I mean, yeah, exactly. So the slides will get into that. But I'm happy if you have any questions about them. If anything is not clear, just let me know.
Great, yeah. If you have questions, ask them. Otherwise, let's keep going.
Yeah, that's fine. Great. So when I talk about Topologic, I tell people that like my biggest challenge is first of all to explain to you what it is that it does, and then why. Once you know what it does, like why does that matter? You know, like so the so what question. And it's difficult because Topologic is, different than other pieces of software. That's not your usual kind of parametric design thing, or it kind of automates some kind of task in Revit or something like that. It does these types of things, but it's based on a different concept. And if we take a kind of a step back, it really talks about these three concepts that you see here on the screen: spatiality, abstraction, and awareness. And I'll explain each one of them with an example. So the idea of spatiality, and the reason we did Topologic, is that both Robert and myself were genuinely unhappy with the direction that BIM is taking. BIM is fantastic and it solves a lot of problems, but in doing so, they forgot about architectural design and what we care most about, which is space. The idea of configuring and making sure that space is as best as it can be in a way, kind of in a piece of architecture. So BIM allows you to organize your project, put all the equipment in there, track everything. It's really fantastic for, putting the building fabric together. But the idea of space is very poorly represented, very poorly manipulated. It does not actually it's not addressed in a BIM system. So we wanted a system that talks fundamentally about space, and to imbue that space with, I call it semantics. A friend of mine, Miguel, calls it information or informational architecture, and I'll show some of his work. But we wanted something that enhances the representation of space in BIM systems, and still connected, obviously, to BIM systems. To BIM systems.
Mm-hmm.
So that's the spatiality. The other problem the other kind of concern we had about BIM is that they ask you to create complexity first, not to create something simple, strategic, abstract, and then create complexity, like I showed in the first slide. They ask you to immediately put the fenestration, the railings, the solar panels even here, all the walls. You need to figure out what they are made out of. And they tell you to then go to an abstract model when you want to do something like energy analysis. So we called it in the proposal reversing the arrow. So basically, we want to reverse the arrow and say we want to set out very simple but rigorous models, and then let the software or humans, mainly probably software is going to be, as I said, better at it, to kind of populate the strategic model, this ghost model, with all the BIM components. And that's the point where we have reached now.
So you're starting with it really basic and then adding the complexity as you go instead of having to define everything at the get-go.
Exactly. But when we talk about something basic, it's not that it's a dumb model. It's actually a very intelligent model because it's imbued with information. It's imbued with topological information, how things are connected to each other, but it's also imbued with semantic information. What is this space about? And space, in our definition in Topologic, can be filled with anything. We don't make a judgment that space is a void or it's filled with air. It could be filled with concrete or gypsum board or a door or something like that, or water or gas. So a cell in a kind of a cell complex, in a kind of conglomeration of cells, can be anything, can be solid or air or void or whatever you want. You can put that information in the cell itself. So the third leg of this is the idea of awareness. And what we noticed is that awareness in BIM systems is very ad hoc. So this is my favorite modeling system before I started Topologic. It's 3D Studio Max. I've cut my teeth on that. I teach it to my students still in some cases. If you build these cubes in 3D Studio Max, and you go to one of these cubes and say, ask it a question, say, who's on top of you, who's below you, who's to your left, who's to your right, who's to your north, to the south, it doesn't know. It doesn't know how to answer that question because it's just a display list, as you can see here, of 13 cubes. In Topologic, you can ask that question and it can answer that question for you. It can tell you, I have 3 cells, let's say, that are my neighbors and I share faces with them, I share lines with them. So it can answer these questions. And that becomes really important. For example, for pathfinding, because you can now go from one room to another room because it knows which room is next to it. I'm not saying that BIM systems cannot do that, and I'm sure people will point out to some plugin here and there, some piece of software that does these things. But it is always done in an ad hoc way. We decided to build it into the DNA of Topologic. It's based on these types of concepts. So you've heard me talk about manifold and non-manifold. What does that mean? That always trips people up. It's very, very simple. A manifold geometry, which is mostly all your CAD systems that you are using right now, are based on manifold geometry or solid representation of objects. Basically, every point on the surface divides the world into 2 states. Either you are outside in the void or you're inside the solid of the object. And that's why it's called actually a 2-manifold, and that's called a manifold for short. When that situation is violated, when a point is no longer just the kind of in between 2 spaces or 2 worlds, maybe it's between 3 worlds or 4 worlds even, that becomes a non-manifold object. So let me show you some examples of that. So if you take a look at these objects here, and imagine a point sitting on one of the lines that kind of maybe the one, if we look at the one on the right, the one that divides the prism into 2 cells, just imagine a point sitting on that line on top. That point is dividing the world. It sits between 3 worlds, the void outside, and then the cell on the left, and then the cell on the right. So all of a sudden, you have points that are non-manifold. They are 3-manifold in this case. So in Topologic, we can represent objects like this without them being considered an error. If you are 3D printing non-manifold objects, the software will complain that it has non-manifold edges because they have like wing edges, or there's a gap, or the mesh is leaking, or it's not closed correctly. We embrace that kind of situation and we deal with it fully. And that's what allows us to deal with non-manifold topology in Topologic. So we created this thing called Topologic, and we gave it the tagline to build something connected correctly and then have the software analyze the final solution. So Topologic is built on these elements. It has these classes in C++, going from vertex to edge to wire. If you close the wires, you get a face. You could join the faces together to get a shell. You close the faces of the shell, or if you have a closed shell, you get a cell. That's our main kind of bread and butter in a way. That's our main component. And a cell complex is when you put these cells together, almost like soap bubbles, and they share faces. That becomes a cell complex. And then a cluster, we added a cluster that allows you to mix and match all of these objects together. On top of these, we added these kind of things that you see on the right. An aperture is basically a special kind of face that represents an opening in a face. So you can like do windows and doors, for example. Content and context, I'm going to skip that, but basically, well, let me explain it really quickly. You can have a window as part of a wall. So you can say this window exists in the context of a wall. But this window is also part of a room, right? So it also exists in a different context, which is the context of the room. So we have multiple contexts, and the room can have then contents. The room can have walls, can have windows, can have furniture. So you can add them to the content system of a space. Dictionaries allow you to do user customized things. So you can put the price of something, or the manufacturer or something, or the some information about what this object is. So you can put arbitrary information in a dictionary. And then graph is really pure topology. It is made out of nodes and edges. and it kind of can represent the connectivity in a cell complex, and I will show you that. For those of you who are more inclined technically, basically we're using Open Cascade at the bottom. Topologic core is written in C++, and then on top of that we have written Topologic Dynamo and Topologic Grasshopper, and now we have other things I'll talk about. Those are written in C#, and then on top of that we did domain-specific software, and they are all hosted by Visual Data Flow Programming. More recently, and apologies for the graphics, more recently we've converted Topologic Core. It's C++ still, but we interface it using something called CPPYY. We made it into a Python module, which opened the door to FreeCAD and Blender, which are open source and free. And I will show you SphereChalk, which is like a Grasshopper clone for Blender. It's really fantastic. And what you see there is that you can have a full stack, which is 100% free and open source. And that was what we promised the Leverhome, is that we would deliver a free and open source piece of software. So the basic idea is that we go from a topologic model, which is, as I said, lightweight but very rigorous, and we use it as a driver to build on top of it either a building fabric model, or we can do energy analysis, or a structural analysis model, or a spatial reasoning model. So this is another kind of image of basically the same concept. And obviously, if you have these models, you can do multi-criteria optimization. So Topologic allows you to do full spatial and component resolution. So basically, there are no overlapping faces, no overlapping vertices or edges. Everything gets resolved fully. So in this case, you have a shaft or a kind of an atrium in the middle that's being imposed on another cell complex, and you see how it kind of erases and things re-emerge out of it as it moves through. It's completely resolved spatially.
So what happens to the faces at those edges?
So basically, it all gets through a Boolean operation. They all get trimmed and cut correctly, and there's a single face inside this construct. There's never two faces that are overlapping. So if you wanted to, let's say, count the area of interior walls in order to like figure out how much paint to buy, or if these horizontal lines are beams and you wanted to count how many beams you have, you just count them. You just ask it, how many horizontal edges do you have? So there's never redundancy. There's never kind of overlapping entities.
I think there's a lot of cheering going on. I had a question here, which I think is pretty relevant. For your Python implementation, is that Python 2 or Python 3 or both?
Oh, Python 3, of course. We left Python 2 behind now. It's done.
It's also no longer supported, right? In general.
No longer supported. All right.
Yes, definitely. Let's keep.
Okay.
Yeah, sorry, my bad.
Yeah, sorry. No, I want to make sure that the questions are answered. So very quickly, because I know there's a lot to cover here, but basically what you are seeing here on the screen is what we call a cell complex, which is a fancy word for saying a group of cells that are connected to each other, basically. But as I said, they are completely resolved. And in this case, we picked at random one cell, and we highlighted it in yellow. So that cell, as you can see here on the left side, is cell index 20. It just happened to be that cell. And we asked it to give us its adjacent cells. We just asked it for its neighbors. And it knows them. It just can give you that answer very, very quickly. And it says, okay, I have 5 cells. I have one on my left, I have one on my right, I have one on top and one at the bottom. And then I'm also adjacent to this like large cell that is in the center of the building that's adjacent to all this in the cells in the building. And it gives you those 5 cells, and then we decide to convert them back into dynamo geometry and color them in translucent red. So the idea is that you can ask questions of a building and it can give you really meaningful answers. Same thing, you can take 2 cells in this building and ask, what do you share in terms of faces? What do you share in terms of lines? what do you share in terms of vertices, and it will answer those questions. It will give you a list of vertices, a list of lines. And as I said, I mentioned the graph. Basically, if you know about graph theory, we implemented fully graph theory. And the idea of a dual graph is that it is kind of the twin of the building. It kind of gives you the how it is connected. So in this case, the graph is a wire where the vertices or the points are the centroids of the cells, and the edges are going between cells that are that share a face, basically. So you get a different interpretation of your building through this graph. This allows you to do all sorts of things, including like path planning or any kind of analysis. And we have other options that allow you to create different paths. So you can tell it, for example, only connect if there is a door between the two rooms, or please connect to the outside windows, etc. And this is the one that is really unique about Topologic. And this is a bit difficult to understand sometimes, but I'll try my best to explain it. As I said, cells can have dictionaries, which you can put, let's say, you can say, I have retail, I have offices in yellow, and then I have residential units on top. So I have 3 cells stacked on top of each other before they are subdivided, right? So you can put 3 dictionaries in each cell. Now, when you go ahead and slice your building using Topologic slice mechanism, the new cells that have been sliced, now I've generated like tens of new cells, they know their parent cell, meaning that the dictionary kind of survives the Boolean operation and ends up being placed or copied into all the children's cells that were created. Not only is it one-to-one, but it's also many-to-one. So for example, if a cell has been created, a new cell has been created as an intersection of 2 parent cells, it inherits, very naturally, it inherits the dictionaries of the 2 parents. So if I have an A and a B cell and I intersect them, the intersection will have a dictionary which is the sum of the 2 parent dictionaries. And that becomes really, really powerful for things like, let's say your design has an intersection between a dining room and a kitchen. And then you say, oh, I have a cell that is an intersection of a dining room and a kitchen. It tells you that it is. And then you can make that into a breakfast area. I mean, this is a very simple example, obviously. But this kind of survival of the dictionaries and the transfer of dictionaries through Boolean operations has proven to be really powerful. And I'll show work of Miguel, who really kind of pushed it to the nth limit. And he's doing his PhD around these types of concepts. So the other thing is topological awareness, in the sense that entities in these topologies know what they are adjacent to. As I said, they can ask these questions. And because these things have dictionaries, you can find out whether a wall is adjacent to one cell. That means it's an external wall, so you can color it yellow. If it is between 2 small cells, like 2 offices, you can color it blue. And if it's between a small cell and a big cell, you can color it red. So what you are seeing here is actually one entity, not 2, even though, of course, I'm using a cube to create it generatively, but I am asking the end result to answer these simple questions. How many cells are you adjacent to, and what type of cells are you adjacent to? And I'm classifying the walls based on the answers that I'm getting from that cell. And it's that power of information that stays with the system that's really interesting here. This one was because I saw that Revit had done intelligent 3D pathfinding, but they limited it only to 1 floor. They cannot handle stairs and handle lifts, or elevators. So I went ahead and took a Revit model, put it in Topologic, and I used some plugins for visibility graphs and combined it with our graph. And then we were able to create a fully 3D, it can even climb up the stairs, fully 3D, shortest path between any 2 rooms. And that all is derived from it.
Yeah, and I don't know, I'm getting a little bit of echo whenever I talk, so I'm trying to be careful not to talk over you. But there's some interesting conversation going here. I'm going to let the conversation continue, and we'll get to it in a moment. But this kind of connection that you're showing seems almost inherent to this kind of system where everything knows its connections. right? Like a diagram or a map or a shortest path is almost, it's almost like inherent if everything knows its connection system. I mean, I'm sure there's more involved, but that seems to be very obvious in what I'm seeing.
Yes, that's exactly right. In the connectivity is embedded in the system. It's not, we call it, it's not ad hoc. It's not something that you have to write, let's say, a little Python script or do something, on the fly to make it work. It is part and parcel of the DNA of Topologic. That's why it's called Topologic. As long as you can build a cell complex, the cells in a cell complex know about their adjacent cells. If you build a shell, just a 2D shell or a 3D shell, like let's say origami, the faces also know about the faces that they share edges with. If you build a wire, the edges in the wire know which ones are adjacent to them or they share vertices with. So that kind of connectivity goes from the very 2D all the way to 3D. But it's inherent in the system, definitely.
And in the situations like you were showing a little bit with that elevator shaft walking through the building, if you have a large surface or a large line and smaller lines that intersect it, what's your result out of that? Is it kind of this dictionary of there was a larger line and now there's these smaller pieces, but there's no kind of duplicate lines, or do you end up with both?
So if they are completely touching, we resolve that. So there will be no surfaces that are duplicated, no lines, no edges that will be duplicated. The problem with Revit models, and Revit models are great. I mean, I have nothing really, nothing bad to say about, they serve their purposes, but they pose a problem for us because while you can get center lines and you can get rooms, etc., they don't touch, right? There's always the gap of the wall. So if you don't include the walls, it can become really difficult. We have solved it in plan because we can get center lines from Revit. That's absolutely fine. But in floors, it becomes really difficult because there is the gap of the slab between rooms. But we were able to. I think I solved it here with a little bit of trickery, and I was able to solve this kind of connectivity between them because I did not really need to go from floor to floor through a slab. I needed to go through a set of stairs, right, or an elevator. So those already connect the two spaces, and I can intersect them, and I can just go through them as you would usually. But I wouldn't just simply be able to go like through the ceiling and into the other room, which you shouldn't go do anyway.
Yeah. Well, I know Autodesk is watching this, so maybe they can give us that functionality in the API of the true center, those reference planes of the of the different surfaces that we're working
I
with,
mean,
like the walls.
one thing I used for sure here is that the doors in Revit, you can check a box and you can ask the doors to store in them which two rooms they connect. It's obviously a lot of people do that and they need that information. But as I said, it is not. I mean, I would assume a door should always know what rooms they connect. I mean, that should be the default. But I found out when I was, and I'm not a Revit expert, but I found out to turn that on in order to get the information out of the doors. But the visibility graph that you see in the lower right corner is really what is important here. Just going on really quickly, because I want to get to some interesting case studies. Some multi-objective optimization we've done when Refinery was first announced. So we use Topologic with that because Topologic is linked to Energy Plus and Open Studio, very much like the Ladybug tools. It's a much more primitive way, I would say. It's not like the Ladybug tools. I would recommend you use Ladybug for these types of things. But it has Topologic energy in it, so we used it with Refinery. This is again Topologic energy, which can give you the cooling loads, and you can play these what-if analyses. This is normal stuff here. We connected it to a fire simulation, to a piece of software called FDS. And we used the cell complex to kind of code in all the doors that are in between. So this is obviously not a very realistic building, but you can talk about how the smoke is spreading in a building and how the temperature is spreading as well, is getting higher. So it allowed us to to kind of create a very simple model that gets simulated for fire. And we connected that fire simulation now to artificial intelligence, to reinforcement learning in particular. We published a paper on it. So in this case, you see this agent, he's this yellow cone, trying to find the fire exits, which are these green spheres at the bottom. At the beginning, it's very, it's rubbish. It doesn't know how to find them, but then it learns to find them, and before the fire spreads. And we applied the same test on the Revit sample building. So basically, you see this agent is the purple cylinder. It learns as the fire is spreading on the second floor. It has learned to duck down, go through, and find the exits, which are these green spheres at the bottom in the basement, and kind of exit to safety. So Topologic can help you with these types of things. It's all because it's pathfinding and doing all of that. So I want to show these 4 case studies, and I'll start. I did them somewhat in a kind of chronological order. So the first one is Mikhail de Gonziak. He was with Bureau Happold. That's how I met him, because Bureau Happold was one of our industrial partners, and he moved to Horlia in Bristol, and he now has integrated Topologic in something called SAM. So I really advise you to all to download it. It's open source. SAM is like glue software. It is running in Grasshopper and connects all sorts of analysis software to each other, and they use Topologic as the kind of the engine to build consistent and clean energy models. So he came over and we gave some workshops together. So he just sent me this today, actually. I asked him for the latest. So he now takes Topologic and can slice it and can organize all the faces, whether they're roofs or walls, etc. And he can create these energy models for Energy Plus. The other person who's doing really amazing stuff is Ahmed Al-Tahlawi, who again I met on LinkedIn when I asked for help, and he offered to help with Topologic, and we ended up collaborating. He's with iPro Consult in Germany, and I had started a workflow where I am taking test fit models and trying to move them to Dynamo. And with his help, we are now able to move them all the way to Revit. But they're not just simple models. As you can see here, the color coding is fully informational. Every surface in the test fit model is fully embedded with information about whether it is a wall between 2 units, whether it's a slab or a ceiling. But not only that, the exterior walls, as you can see in the lower left corner, because that's important for Revit users, I'm told, they're not segmented. They are like continuous external walls. So that kind of there's an intelligence in the handling of the elements, so that you can get complete BIM elements at the very end. I'm not showing the Revit model yet, but we have it. We have it internally ready. I'm going to skip but you please look him up on Twitter. He's really fantastic, and we have some new projects that we're working on as well, trying to look for funding for those. And this is who I mentioned earlier, Miguel Velgas Ballesta. I hope I'm saying the name correctly. And this is the latest image that he shared on Twitter. So what you see on the left side is a Topologic model that has, kind of embedded in it a full information about what these spaces are, and he can also move these things together. It's just like a wire diagram that he can move, and in real time reassign semantics or information to the spaces, and because of that, it will reinterpret the model differently and will give you a different BIM result. So what you see here on the right is again this kind of BIM interpretation of the information model. It goes much deeper. I don't sometimes understand what he's talking about. He's doing his PhD on it, and it goes really advanced, but I hope I did it justice. This is the one that floored me completely. This is Bruno, as I showed in the beginning. Again, in the top row, and apologies for the formatting of the images, I kind of slapped them on there really quickly. But the top left is the Topologic model. So it is just simply a cube, and then just a bunch of faces that are flying in the air and intersecting and slicing this cube. And based on that, He creates cells, he creates floors, he creates parapets, walls, windows. Everything gets completely populated and resolved fully, and you get IFC models at the very end. And he doesn't do any manual work other than working with the Topologic model at the beginning. The ones at the bottom, this is called Topologic Alley, which I love. I told them I love to live on Topologic Alley. Again, it's this type of simple cubes, but then you get something that is really realistic at the end. That to me,
Yeah.
in terms of that,
I wanted to come back to one of those just to understand them a little bit more. One of the questions that came up is, why is non-manifold topology important for this kind of functionality? I don't know if we were talking about something specific there or not, but I want to kind of expand on that. And looking at this top two images here, I think really help. So looking at the top left one that I'm seeing, that's the one with the planes cutting through the building, right?
Yes.
And the one on the right is kind of your finished product. Obviously, with using Grasshopper and typical, I guess, manifold topology kind of strategies, I see something where I'm seeing a plane that I could reference and create rules around and create those windows and the logic to create those windows within the distance. What about Topologic makes this particular thing specific? And feel free to just answer the general question of why is non-manifold topology important for this functionality, but maybe you're kind of seeing the question that I'm kind of getting at. If not, we talk about it.
Yeah, no, that's fine. No, I'm not. I don't see the chat, so I'll just respond to your question on it. Basically, as I said before, a lot of the stuff you can do in ad hoc ways, and you can supplement it. But what happens is that you will get certain capabilities. Somebody might write a plugin, or you might find a little workflow that does it. And then there is a dead end, or there's another capability that you don't have access to. What happens with non-manifold is that you can do two things. You can represent objects that have interior partitions as part of the representation of the object. So you do not have to worry about, let's say I have a cube. So a cube can have as many interior partitions in it as you want, and it will be fully resolved. We call that a cell complex. It can also have objects that are of different dimensionality. So you can have a cube that has a winged edge inside of it, or an edge or a vertex that's floating in midair, or connected to only part of the face or something like that. We do not make any, we don't make trouble about that. It's all part of the non-manifold topology, and you can find your way through those things. So it is really powerful to be able to think of a building as this kind of volume that gets subdivided by faces, and then you get the result. But also, when you get that result, you can, as I said, you can ask questions of these cells. So when you have a cell, it's not just a cube that happens to be sitting next to another cube. It knows the adjacency information. And that becomes really powerful because let's say you're designing a hospital and you sliced it up into rooms, and then you assigned one room to be an X-ray room. That's where the X-ray machine, and right next to it is a waiting room, right? That wall needs to know that it is between an X-ray machine and a waiting room, because it will probably need to have some kind of lead paneling or something like that to protect the people in the waiting room from radiation. Or if it is if it is an exterior wall or an interior wall. So that information is always there and available.
That kind of relational information really becomes innate to how the whole system really works.
Yes, exactly. Yeah. Exactly. You don't have to write ad hoc little plugins all the time, or import little
What's
workflows
next to this wall?
That.
What's next to this wall exactly? Thomas Voigt, which I'm sure you know, is asking, yes, do you think it's possible that Autodesk creates tools in an early design environment in Revit to create such spaces and logic between cells, maybe without using Dynamo? Would it make sense to have something like this for them?
Can Autodesk do that?
Will they? Do you think? This is a theoretical. You can say whatever you want. What do you think?
They can. Right. First of all, Autodesk can do this because they had it. I mean, this is the really frustrating thing is that in 2013, and Aparajit Pratap will tell you this, they had non-manifold. The ASM kernel that serves Dynamo and serves Revit is non-manifold and has all that capability. They just needed somebody to write all the methods on top of it, like we did. It took us $300,000 or pounds, excuse me, 300,000 pounds and 3 years
Which is
to do it.
$500,000. So no, I'm just kidding.
It's about 400,000, but yeah,
Yeah.
it's not a lot of money. But they do have the capability if they have the will to do it.
Mm-hmm.
Will they do it? I believe that non-manifold topology and the idea of topology is starting to take hold. I think a lot of people hear about it. They are watching me. They tell me they're watching me. Despot is watching me. Hyper is watching me, which is nice. It's really flattering to know that they are interested in this technology and they're just waiting to see where it goes.
And it's particularly fascinating for us. We at Your Desk, even though we are Your Desk University, don't do a lot of theory. So I like kind of stretching our bounds a little bit here, and thanks for that. Another question that came here is on that fire simulator you were showing. This is from Jacob Small, actually, who,
Yes, I do.
Hi, Jacob. He asks, is that opening capacity, is that the ability to have those openings that you were showing, is that for any kind of CFD tool? Could that be fully developed? What are the limitations of the openings? And I'm guessing, connecting with what you were saying earlier, that those openings are that object in your topology model that you were describing, where the wall has an opening, an aperture. Thank you.
Yes, indeed. So basically, from this cell complex that has apertures embedded, that's all so what you see here on the right side is what we modeled in Topologic. From that, we were able to thicken the walls and do a Boolean subtraction to get the openings, as you can see here. So we encoded, there was a little script that encoded that into a model that FDS would know about, basically a mesh of some sort. This has been a few years now, so I would have to dig up the software on it. And once you have that model, you can do the simulation. But the idea is that we did not need to create a very sophisticated model. We could have. There's nothing, anybody can just model this. But we were able to do this. What is really interesting about this is perhaps not the FDS simulation. This is great, but that you could do it with any kind of mesh model from any CAD system. But this one allowed us to have the navigation very easily done for the agent. Because we can, when we are talking about an agent trying to move in the 3D world, we did not have to do anything extra to say, okay, now you have two options, right? You are in this room, room 8, and you have two options. You can either go to the left or to the right or up or down. So basically, because the cell complex has all that topological information, we can tell it where to go. So when it reaches the end of the room, it can't go any further. It has to turn left, etc. So that all comes naturally.
Originally, when you were showing this, I thought that was a little firefighter that walked around and tried to put the fires out. But I get how you're working in the opposite direction of that, trying to escape the fire.
This is about residents trying to escape.
An interesting little machine learning algorithm. Did we maybe tease a small live demo of this?
Sure. Why not? Let's blow up the computer. Sure. To me, this interface is now, I love Dynamo. This is where it started. But it's starting to look to me a little bit dated, but I'll tell you why in a second. So basically, this is one of the tutorials you find on the website. I just don't get scared by all of this. This is really me trying to create geometry from scratch. So this is like cell by cell, face by face, all of that. That's why it's so huge. And it's not repetitive. It's just, or it's not like in a loop or anything like that. It just, copy paste a lot of it. But basically, let me just display the cell complex.
Don't worry, we're not going to judge your Dynamo skills as long as you don't judge our Topologic skills.
So basically, here's your cell complex. So if you count the number of edges here, and you say, like, I want to order like beams and columns, so you have exactly 132 edges right here. So there are no duplications. It's exactly as you would count them in terms of like the smallest segments that you see here. Like if we wanted to find the cell, so I have here the cell complex. I can say topology dot cells. Oh, sorry, I typed correctly. And I run it one more time. So I have 25 cells. It's basically 6 stories, four cells per story, plus the one in the middle, gives you 24 plus 1, 25, exactly. So if I do, let's say, a code block, and I say, give me cell 20, as I did in the slides. So I get cell 20 here. I need to run it, sorry. So that is a topologic cell, that's one of them. So I can say topology.geometry to be able to see it. The thing is that Topologic does not draw anything to the screen on purpose because we think it's wasteful to keep like drawing stuff. So that's that cell, right? It's away from us. So you can choose which cell you want. So let's choose another one. Let's say 18. So that's 18. That's the one we did in the actual slides. So if I say cell dot adjacent cells here, so I should get 5 cells as the adjacent cells. And run it one more time. And here are the 5 cells. So if I do topology.geometry on those, just to draw them.
And for those who've worked in Dynamo, they know how heavy and showing all those visuals can be. So I can understand if you're trying to build something that's really fast and sleek, you would want to skip those steps. And those are all the adjacent cells, including the elevator shaft, which I mean I get, but I don't think I would have connected with it right away.
Yeah, because they all kind of have share a face. So if I change the cell from 18 to let's say 14, and then run one more time, now it is this cell at the bottom probably. If I choose it, it's this one, and it has those cells. So any cell I choose, it will immediately update.
And really, you're working on expanding and working on the functionality of this engine behind all this geometry so that it can be incorporated into Dynamo, into Grasshopper, into Blender BIM, which I'm not. I'm learning, a little bit more familiar with. I know you're digging into it a little bit, and we've had some promises of speakers wanting to come on and share a little bit more with us about it as well.
Yes, I have to be careful. It's not Blender BIM yet. I always use the word
Blender,
yet.
Of course.
It's Blender because Blender BIM is a plugin and it's a fantastic plugin. And we are doing our hardest to get to it. But let me show you Topologic in Blender. And this is this is pre-alpha software, I would even call it. But this is basically Topologic Python, or Topologic Pi as I call it, running in SphereChalk in Blender. So what you see, the yellow here is the cell complex. And the white stuff, so like the sliced things, the solids, are basically, I bake the geometry and I move them out of there. So basically, this solid was sliced by these planes. So let me just show you the planes. So these are the planes like this. So they sliced this object. And because they sliced them, you have now 8 cells. And you can circle through them. And basically what you can do is you can, let's say, bake one of them and then select it and move it out of the way. Get a copy of it. And then you can move to a different cell, bake it. I'm still learning Blender. I'm not a Blender person, but the first time I used it, it was so complex. But now it's looking more and more like 3D Studio Max, so I'm getting used to it. But Topologic in Blender has all these methods now written, and I'm writing more as we go every day. So that's kind of what consumes my time these days, is writing these methods in Python.
And so this is a Python module, so it can be accessed from any Python. And you were saying, I think Python 3, that people can just access it. So whether they're working in Jupyter Notebook or any other place, I imagine that it's what kind of visualization? Because I think that becomes always the complexity of working with geometry in a Python area without the visualization. How do you cross over that
Right.
border?
Without in Python there is no visualization.
Mm-hmm.
Because I mean right now you saw I loaded it into a Python console, so I can say v equals to topologic. Sorry, I have to do topologic.
No worries. I'm going to try to zoom in here so people can see that.
Oh, can you see that? Yeah. Vertex dot by coordinates. Sorry, it's going to be a lot of typing, obviously. 10, 20, 30. As Theo always says, I like 10, 20, 30. Also, I do actually. So if I say print v dot the x coordinate, that's 10. So the full topologic is available, and you can import, let's say, BREP files from FreeCAD. You can output them. You can. I mean, we just simply moved things between FreeCAD and Blender through BREP, through Topologic. You can create an edge, etc. So the full API is available, but in order to translate geometry into Topologic, that you have to write some code for that, obviously.
Yeah. I want to ask another kind of off-the-wall question, but everything you've been showing is geometric. But relational aspects, it seems like you're working almost on a relational database, and maybe I'm oversimplifying it, but there's these relationships that are getting created around systems. And I think if we were to go back to your slide, which probably now wouldn't work, I'm actually going to switch to the no slide view here for a second because we've got a couple of minutes. And I've already zoomed you out so much, or zoomed in your screen. But does a similar system work without the geometry, or is the geometry innate to what you're providing?
The geometry is innate to it because we are building on top of something called Open Cascade. Mm-hmm. So Open Cascade is a non-manifold 3D geometry kernel. FreeCAD is based on Open Cascade. There are other pieces of software. IFC OpenShell is based on Open Cascade. So we built some relationships in addition to what Open Cascade gave us, but most of it is actually allowed and handled by Open Cascade.
Yep. Curved geometry, we got a question around that. And I actually did get your screen zoomed back out. So if you want to go back to that slide that shows the kind of the cell complex and how the pieces work together, I thought that might be a good one to end on as we present. But does topology work with NURBS or curved surfaces, and how does it handle those types of manifolds? Those types of non-manifolds?
Non-manifolds and manifolds. Obviously, non-manifolds is like a superset. But yes, in short, Topologic handles NURB surfaces absolutely fully. It's based on BREPs. So BREPs can be anything, can be quite complex. I usually use flat surfaces, etc., just for speed. The thing with with the Blender is that we have not yet supported NURBS in Blender. That's coming soon.
All right.
But in Dynamo, it is in Dynamo and Grasshopper, you can do extremely complex NURB surfaces and it will intersect them correctly and everything. Yeah.
Yeah. Well, with that, I think we've gotten through most of the questions. If we missed your question, Wassim is in the Slack channel. You can access our Slack channel by going to our website, yourdeskuniversity.com, scrolling to the bottom and joining us. And we invite you to come in there, bring your questions, and be a part of the community. And thank you, everyone, for your questions, for participating. Wassim, thank you for being a part of this. It's great to have you, and I'm grateful to the time and effort that you're putting into this.
You're welcome. Thank you for having me, guys, and thank you for the questions. Really fantastic to share my work with you.
Awesome.